Good afternoon, colleagues, and thank you for putting together this session. Yes, I've been introduced as Shadrach Mkansi, Manager for Public Engagement Platforms here at SASTA. Science Week is basically a project that has been put together by the Department of Science and Innovation and Technology to celebrate science, technology, engineering, mathematics, and innovation on an annual basis, and which is done nationally, and it's addressing all communities, all sciences, and ensuring that there is a promotion and a public awareness of the value that science is playing in our lives. And this year we have chosen a theme of living in a high-tech world. Should we be concerned? And this theme is helping us to appreciate the benefits of technology, how it has improved our living conditions worldwide, and the drawbacks of relying too much on it. It is giving us an opportunity to display the transdisciplinary from the natural sciences, social sciences, and human sciences to inform the future of technology. And this session is going to particularly look at understanding local and global societal dependency on technology. And I believe that through this session, we'll be able to learn a lot in terms of how much we depend on technology and how is that technology affecting us locally and also affecting us globally, and how it has changed the society, the families, the communities. And I'm not going to dwell much, but I'm just giving the gist of what we thought. And we are giving it to SAICE to say, over to you, SAICE, and let's have a discussion, let's have a conversation with regards to this particular topic of dependency on technology. And I want to welcome everyone who has managed to join. We've got about 140 people who have joined the session. And I believe that we're going to have a fruitful conversation led by SAICE. And Tom, over to you and your team, and you can take us through the session. Thank you very much.
Thank you very much, Shadrach, and also to the other SASTA colleagues who are in attendance. We do appreciate the relationship with yourselves, and as SAICE, we are a learned society, always in and available to promote technology and in particular civil engineering. Just for those that were unaware, the webinar is scheduled to run until 17:30, possibly a little bit beyond, and will therefore be quite jam-packed. If you have any questions or comments or compliments or complaints, please pop them in the chat. And if I and the team, the panel, have a little bit of time after the three presentations to attend to them, we will do so in a Q&A session. And failing which, if I can ask the three panel members when they're not presenting, if there's a question that pops up that they are able to answer or respond to, they are all very esteemed in their own rights, then if you can please do so. It's now my very distinct pleasure to introduce you to the first of our speakers for tonight. That is Mr. Brian Downey. Although Brian needs little introduction to the SAICE family, having served as our president in 2019, for those who do not know him, just a little bit of background, and Brian has specifically shied away from his working life, but has given me very brief snippets of where he's come from and where he has been. He was born in Ireland and graduated from Queen's University in Belfast. He doesn't say anything about whether he had to duck bombs and other things at the time, but he survived. After cutting his teeth in construction and bridge design, he graduated to the project management field, in which he then ran a wide variety of transport and major infrastructure projects. His involvement in SAICE coincided with South Africa's transition to democracy, so over 30 years ago, when he became the chairman of the Durban branch. and his volunteer involvement directly with SAICE culminated when he became the president of SAICE in 2019, as I previously mentioned. He is a student of future technology, mentoring young graduates in 3D printing and drone technology. Brian's topic for today, and just by the way, Brian is presenting to us from New Zealand, so it's something like 2 or 3 o'clock in the morning, which shows his commitment not only to technology, but also to SAICE and the SAICE network. Brian's topic tonight is the evolution, or in the morning if you're in New Zealand, the evolution of robotics and AI from ancient automations to intelligent machines. Please show your digital appreciation by welcoming him with a clap. Thank you, Brian. Over to you.
Okay, I'm now unmuted. Thank you, Tom, for the introduction. I will now present my share screen. I've got the audio on. Start the broadcast. 3, 2, 1.
Okay, we can see your desktop, Brian. There we go.
Okay, can you see my first screen?
We can see your first slide. You're good to go. Thanks, Brian.
Okay, wonderful, Tom. I'm glad we had the trial section. I think for everybody in the meeting, it's really significant that the world media, having featured an occasional article in artificial intelligence 3 years ago, moved quickly to a major focus with the launch of ChatGPT 2 years ago. And equally, robotics is about to roll out the same trajectory. And so our subtitle is particularly important: from ancient automatons to intelligent machines. It may come as a surprise to people, but robotics was way ahead of artificial intelligence. And in the 16th century, the famous artist Leonardo da Vinci, who painted the Mona Lisa, and who was a very involved inventor, having invented or foreseen such machines as the helicopters and parachutes, chose to say that he believed that the day will come when automatons, because of course they were manually driven, not digitally driven, will be able to mimic almost any human activity, whether it be spinning, weaving, playing music, or perhaps even speaking. Very prescient words, I must say. So it was another 4 centuries before we saw the first digital computer built in 1942. That was the Atanasoff Berry computer. It played a very important part in the Second World War with the evolution of the cracking of the German code and the winning of the war by the Allies. We then had a period of some 50 years where the computer age, you'll see in the top right-hand corner, the computer age came to fruition. That was as the servers and the backbone of the internet was being built. At first, we communicated via telephone lines at 1 kilobit a second, which meant that files were transmitted very, very slowly. To transmit one photograph would have taken quite a few minutes, never mind a full article. But it was in 1990 that the internet really sprang into life with the introduction of the World Wide Web. And the internet age, which has lasted from 1990 to today, has grown in fits and starts, with many, many companies joining and adding immense value to the knowledge of the world around the world. Perhaps the first inkling that the public had of the value of artificial intelligence was the time that IBM's Deep Blue computer beat the world chess champion, Garry Kasparov. And that was in 1997. It was a significant moment because it displayed the power of digital intelligence, and that is pattern recognition and probability. So the computer Deep Blue had played perhaps 1 billion or 2 games of chess. And when it looked at the pattern that you see on the screen, it recognized it. And it also recognized that the probability of moving the bishop would have resulted in a 56% chance of winning the competition, as opposed to moving a pawn, which would have given you a 46% chance. So Garry Kasparov really didn't stand much of a chance, because Deep Blue was capable of 200 million calculations a second, which is something that the brain has never been able to achieve. We skip forward now to 2014, when people were wondering who was going to win the AI race, Microsoft, Google, or Amazon Web Services. At that stage, there were really only 3 players available. Google was the predominant player. They had 190,000 employees with an annual income of $160,000 billion. Very significant company. And they didn't expect a small company of 500 people, started by Elon Musk and Sam Altman, called OpenAI, to steal the march on them, but that they did. And they worked from 2015 until the launch of ChatGPT. Elon Musk backed out in 2018. He had provided the initial seed funding for OpenAI, and he had recruited many of the boffins who were building this new technology. He therefore was unaware, or only vaguely aware, of what it was happening in the background, and that is that Microsoft had now approached Sam Altman with an offer of 10 billion rand, which later became 13 billion rand, to fund what they wanted no longer to be OpenAI, but a closed artificial intelligence, ChatGPT. This is a view of their data center in California. It's probably on one corridor. There must be many other corridors, but that's what 13 billion rand buys you. And so on the 30th of November 2022, they launched ChatGPT. OpenAI launched ChatGPT. The Times of London called it the world's first truly useful chatbot, a stunningly lifelike conversational language system. And it was truly that. This slide serves to show how quickly the world took up ChatGPT. You'll see at the very top, it took Netflix 3.5 years to reach 1 million users. Halfway down, you'll see that Facebook took 10 months to reach 1 million users. And at the bottom, ChatGPT took 5 days. A really very important indicator of how quickly ChatGPT was adopted by the international community. I'm going to read a little bit. I don't normally read from the screen, but some people may not be able to see. This is the evolution of ChatGPT, which is known generically as generative AI. So artificial intelligence is the field of study. It's about 100 years old. Machine learning quickly followed. That's a branch of AI that focuses on the creation of intelligent machines that learn from data. Deep learning is a subset of machine learning methods based on artificial neural networks. Artificial neural networks are the computer equivalent of the human brain. They almost exactly mimic the processes that take place in the brain, but they do so on a digital basis with electrical inputs. Generative AI, as it was then, is a type of artificial neural network that generates data that is similar to the data it was trained on. And ChatGPT initially was trained on text. So it had read everything that was available on the internet and more. And it was then able to answer questions both in text and in voice. So if you asked it a question on your cell phone, it would reply to you in voice, as well as putting the text on the screen. Of course, they weren't the only ones who were hunting generative AI, and that was the 5 that you see here. They were the key ones. You have OpenAI on the left, just the logo. Gemini was a product of Google. As I said, they had 190,000 employees compared to ChatGPT's 500. Meta is the holding company of Facebook. Copilot is Microsoft's version of artificial intelligence and works quite closely with Word, Excel, and PowerPoint. Claude from Anthropic is a very important part of the artificial intelligence community and is one that I favor. Jensen Huang played a really important role in the evolution of artificial intelligence. He co-founded NVIDIA in 1993, but it was by 2003 when he realized that the product that they were producing, the graphics processor unit, was exactly what artificial intelligence needed to accelerate the growth of artificial intelligence. And I'm going to play you a clip, which I hope you hear, of a statement that he made at the World Government Summit in Dubai earlier this year.
I want to say something, and it's going to sound completely opposite of what people feel. Over the course of the last 10 years, 15 years, almost everybody who sits on a stage like this would tell you it is vital that your children learn computer science. Everybody should learn how to program. And in fact, it's almost exactly the opposite. It is our job to create computing technology such that nobody has to program, and that the programming language is human. Everybody in the world is now a programmer. This is the miracle of artificial intelligence. You now have a computer that will do what you tell it to do. It is vital that we upskill everyone, and the upskilling process, I believe, will be delightful, surprising.
So that's really important. Almost every artificial intelligence large language model uses NVIDIA's chips. That's the H100 chip. It costs 40,000 Rand a chip, and it processes an enormous amount of data on the chip. And in fact, it's really the strength behind artificial intelligence. And you'll see that from 2015 to the launch of ChatGPT 3.5, it took 8 years. And in 2022, when they launched it, it was text only. The development now of the chips that NVIDIA was producing allowed them to take 8 months to move from text only, as you can see in the bottom right, text, images, and video. And video has become the most important element of OpenAI and will drive robotics, which is what we're going to touch on today. So it just gives you a little indication. 8 years for the development of text only, 8 months for the development of text, images, and video. So now generative AI refers to artificial intelligence systems that can create new content, such as text, images, and video, based on the data that they've been trained on. So video, in other words, watching people, is now replacing text as the new data. And Tesla use that in their full self-driving technology, which you'll hear a little bit more about in a minute. And here's a video that explains this.
The reason this version is such a big deal and what you're seeing here is truly incredible is that the car is no longer using the 300,000 lines of human written code that it used to rely on to drive, and instead it's been replaced with a much more simple AI that learns to drive exclusively from video clips. In layman's terms, this means humans no longer manually program the software or even have any ability to tell it how to behave in certain situations, and instead they show the car a massive amount of video clips of real-world driving, which it then tries to mimic. What's truly amazing here, and hard for people to wrap their heads around, is that the car has never been told what lane lines are. No one told it to stop at stop signs or stoplights or even how to navigate construction zones, none of that. It just remembers seeing this kind of situation before and is doing it how it thinks it should be done.
Okay, the reason that that's such an important clip is that in 1 week's time, on the 10th of October, Tesla are launching their new robotaxi. This is just an artist's impression of what he thinks it might look like. I'm certain that it won't look like this, but that's one person's idea. The one thing that it will look like is it won't have a steering wheel. So when you summon with your cell phone a robotaxi, it'll arrive at the position you're standing in, and you climb into the car, you tell it where you want to go, it takes you there and it drops you off, and then it leaves to go and collect somebody else. This will change the use of cars from the present 15% of its time, most cars sit around all day long, to more like 80% of the day, and will enormously increase the ability of cars to service the public, and probably decrease the number of cars necessary on the road. If we look at artificial intelligence in medicine, it plays a really important role, and this is where we are going to see the greatest movement in terms of the human population. At the moment, it's been many years now since artificial intelligence has been able to read an X-ray better than the best radiologist in the world. But more recently now, in fact, just 3 weeks ago, a friend of mine underwent a robotic operation. It was a very intensive operation. And the two surgeons who performed the operation were not sitting like the people who you see here in the room. They were in another room. So they didn't have to scrub up beforehand. The process was very clinical. Those surgeons could then go back to their rooms and or perform another operation as they wished. And even more than that, they could perform an operation across the world. And that is really where we are going to see the biggest change in robotic operations. The ability of anybody in the world to have an operation by the top professional in their discipline. Development of humanoid robots is important because we live in a humanoid world. If you want to walk into a building, you have to open the door. And unless you're shaped like a humanoid robot, you won't be able to do that. This is just a humorous clip of an early day robot carrying somebody from one bed to another. But it's not too distant in the future when lonely people are going to employ the use of a humanoid robot to be their friend. I think many of our elderly people suffer from loneliness. There's nobody to talk to. There's nobody certainly to have an intelligent conversation to. Sophie, the robot on the left, is probably cleverer than any person in the world and can talk about anything you want to. And if the Gogo on the right says, I've got a problem, then Sophie will attend to the problem in a preliminary way. And if she decides that more intensive care is needed, she'll call an ambulance. If you think that that's a long way away, as a robot, such as you see now, it's probably 2 to 3 years away. Already, they have got very basic robots performing this task. And in the future, you'll see that the basic robots will evolve within 5 years to something that is totally lifelike. So when you have a companion sitting with you, for the price of a small car, you can have the look of a real person sitting having tea with you and having a conversation with you about your children, about life in general, anything that you want to talk about, talking about TV programs, whatever. Here's a robot from a year ago cooking a boiled egg. In 6 months' time, that robot will be able to cook an omelette and to clean up afterwards. And the reason for the need for humanoid robots is seen on these two graphs. The one on the right, which is Guatemala, is a very normal country. They've got a growth of young people graduating into the working environment, working their whole lives, supporting their grandparents, and able to do so because of the production in their productive years from 18 through till 65 or perhaps 70, whatever it may be. Whereas Japan on the left is in a very different situation. There, the number of people who are entering the workplace just aren't enough to support the older generation and to do the work that produces the goods and services. This shows South Korea, which is in the worst position in the world. The predictions are that by 2030, they'll drop from 51.2 million to the year 2100, a population of 21.8 million. Now you can understand what that's going to do to any country. Their ability to service the industry and to support the older people is just not going to be there. And so they realize the need for humanoid robots to take over from them. And currently that's exactly what's happening. You'll see that South Korea leads the world in humanoid robots, swiftly followed by Japan and Germany and Sweden. China, by the way, is in 9th position. So they're following very quickly on, and I expect China to overtake most of the rest of the world in humanoid robots. This is the graph of what's going to happen in South Korea. They expect that by 2025, 20% of the workforce is going to be humanoid robots. Or should I say, robots, not all humanoid robots. Because Boston Dynamics is producing a series of robots which can perform many, many different tasks. They may have 2 arms and 2 legs, such as the one on the right, or they may have 4 legs like the one they call Big Dog Robot. And if you look at Big Dog, that can perform many tasks. For example, in an emergency, it can go into a burning building, which a human couldn't go into, and rescue people. There are many tasks that different forms of robotics can do. that humanoid robots won't necessarily be able to do. In fact, there's one called Roomba, not generally used in South Africa, but available in many places around the world. When you go to work in the morning, you switch it on, and it moves around your house or your apartment, vacuuming and cleaning the floors. And by the time you come home at night, everything's sparkling. So AI, robotics, and other forms of smart automation have the potential to bring great economic benefit, contributing up to $15 trillion to global GDP by 2030. That's a statement by the McKinsey Global Institute. You can believe them whether you'd like to or not. And it'll create a world where people work with robots, not like robots. And I think that's important. Just like AI, where the doctors are being told, you will never lose your job to a robot, but you will lose your job to somebody who works with a robot if you do not use a robot. And that's true for all of us. We either embrace this technology and we learn as much as we can, or we fall by the wayside. And so now as we conclude the presentation, I've just shown where we've come from, Homo sapiens 200,000 years ago, to the highlight of what we regard as intelligence, and that's Einstein 100 years ago, to the world where we live in now. And that is that artificial intelligence has long since bypassed the ability of normal people. And what are we going to do when we reach that point, which is called the singularity? And the singularity is where artificial intelligence is more intelligence than the sum of human intelligence. I have a video which tells us a little bit more about that.
In this century, probably, we will be building this hugely consequential thing, which is the first general intelligence that will be smarter than humans. This involves an enormous responsibility. This is like maybe the most important thing that our species will ever have done on this planet, giving birth to this new level of intellect. I'm Nick Bostrom. I'm a professor at Oxford University, where I run the Future of Humanity Institute, with the unusual mandate of trying to think carefully about the really big picture questions for humanity and the future of Earth originating intelligent life. And once you go a little bit beyond human, then you get this feedback loop where the brains doing the AI research will become AIs themselves. Therefore, I think there is a significant chance that we'll have an intelligence explosion. So that within a short period of time, we go from something that was only moderately affecting the world to something that completely transforms the world.
And so, gentlemen and ladies, I have finished my presentation. And obviously, in due course, I'll answer questions.
Thank you very much, Brian, for providing that introduction to what is to come, more relevant to the technical space of civil engineering. I'm going to jump straight into our second presenter for the evening, and that is Mrs. Kim Tim. For those of you who are not aware of who Kim Tim is, she completed her base degree or her first degree at UCT. By the way, she achieved that summa cum laude. She then did an MSc at Stellenbosch, which she also achieved cum laude. She's making all of us look rather dumb, I'm afraid. The majority of her working life has been with BKS, who became ACOM, as a structural engineer, and in which time she spent a lot of her time, obviously, helping young candidates, professionals to become registered, work that she continues to do. Right now, Kim is pursuing a PhD at Stellenbosch University. So she's a full-time student, but also doing a little bit of lecturing and teaching while she is there. She's a multi-talented structural engineer with a deep love of technical engineering, natural and dynamic leader who has always excelled in academia and the consulting industry alike. I think Kim, for those of you who don't know her, she's just got back from presenting a paper at the Digital Concrete 2024 conference, which is a biannual 3D concrete printing conference in Munich. So the information that she's about to share with us is hot off the international stage. Her topic for this evening is 3D concrete printing, technological promise and societal impact. Over to you, Kim.
Thanks very much, Tom. Let me just share the screen and we will go from there. If you can just give me a thumbs up that you can share, see my screen.
We can see and hear. Thanks, Kim.
Wonderful. Okay. I'm slightly concerned by my internet, so I'm not going to put my video on for once, but let me know if there are any problems coming through. Okay, so it's a pleasure to be able to talk to all of you today. As Tom said earlier, feel free to write any questions in the chat. I'll answer them after my presentation, or we can go through them in the panel discussion. So today I have the pleasure of talking to you a little bit about 3D concrete printing, what it means, what we can do with it, and then touching on a few of the possible societal impacts. So it'll start with a bit of an introduction on what it actually is, some similarities and differences between actual conventional concrete and 3D printed concrete, where we use it, maybe cover the costs a little, because everyone always wants to know about the costs, have a look at society and where we're going next. Right, so what is 3D concrete printing? Well, it's officially stated as a cementitious additive manufacturing method for building elements or structures, but in reality, it's actually a very broad category. There are many different types of 3D concrete printing systems, which range in all sorts. You can have layered shotcrete to D-shape methods, binder jetting, flexible molds. All of these are used in different sorts of situations and to create different effects. But what most of you are probably thinking of when I use the expression, it looks something a little more like this. So this is, I would say, a fairly standard extrusion method from 3D concrete printing. In this method, the material is constantly extruded from the nozzle. It's layered to form walls, columns, facades, or even whole buildings, depending on the application that you're looking for. Machine typically runs along its predefined print path, and then it starts the next layer as soon as it finishes the previous layer. For those of you in the audience who've played with the sort of home plastic printers or PLA 3D printers, the concept is very similar to the ones that those follow. You can control the print speed, the length of the path, the characteristics of the material, and the geometry, and adjust all of these in order to create whichever desired effect it is that you are looking for. So we print this through a variety of different ways. The two of the most common systems that this form of printing is done is either through a robotic arm or a gantry printer. The robotic arm typically has 6 degrees of freedom. The different systems have different advantages and disadvantages. So where the robotic arm is very precise and highly versatile, we use it for very complex geometries and intricate work, but it is often limited by its reach. So obviously it has an arc that it can work in, and that means it's typically used for either off-site elements or architectural work or very localized elements it's trying to build. The gantry printer on the other side is a very large-scale additive manufacturing machine. It is typically built for designing for building larger elements or even full buildings themselves. Here, your constraints are limited by the size of the machine itself, and I will say they are getting pretty large now. Double-story, even higher buildings are comfortably within the spec of some of these gantry printers. Concrete printing, is this the same as normal concrete? Does it behave in the same way as conventional concrete that we all know? Well, not exactly, no. It is similar. It has many of the same advantages and disadvantages. but it is also different, not only in the method that it's built, but also in its overall behavior and the characteristics of the printed concrete. So I could spend the next several hours talking about mixed designs and properties. There's a massive amount to know about 3D concrete printing in this way, but well, I don't think that you all have that amount of time, and it's the mixed design part is not my speciality, but I will give you a brief overview. In a lot of ways, there are similar considerations that you need to pay to conventional concrete. You also need to design your mix appropriately for your desired strength. You need to pay attention to your binder content just as you would for conventional concrete. And in fact, in many cases, printed concrete has a higher binder ratio than conventional. And this is something that's receiving quite a lot of research. When you look at things like aggregates, however, it's a little bit more complicated. The majority of the printing that we are doing at the moment is actually being done, it's not actually concrete. It's officially a mortar rather than a concrete, because quite a lot of the aggregates are only up to 4 millimeters, in some places 8 millimeters. There are some printers that are printing standard concrete 16 millimeter, 19 millimeter stone, but they are not the norm for the concrete printers at the moment. And they are often used for slightly different purposes. When it comes to the aggregate in 3D printed concrete, you actually have a bit of a balancing act going on. You want your strength properties and the interlocking and the shear that we know that we need in aggregate in concrete. But at the same point, you want a highly pumpable mix, which doesn't get stuck in the nozzle of a machine. And if the aggregate ends up being too large, then that affects the actual sizes and the dimensions of the layers that you can deposit. So balancing act when it comes to that. Workability. Now, workability is something that we know from conventional concrete, and the workability of 3D printed concrete is even, if anything, more vitally important. And we tend to focus on the terms extrudability and buildability within the 3D concrete world. So extrudability is now the process, the extrusion process is the ability of the concrete to pass through the concrete pump, the transmission pipe, the nozzle, without any actual change in its physical properties. You need to be able to extrude the concrete in a very smooth manner to allow the printer to put the one layer on top of the other one smoothly, evenly, without any irregularities and inconsistencies. At the same point, buildability is also very important. Now, buildability is your ability of the underlying concrete layers to carry the weight of the next concrete layers. So this can also be a bit of a balancing act, because you don't want your sublayers to be deforming excessively from the weight of the layers which are being placed on top of them. But at the same point, you can't make your layer so stiff that when the next print run comes over it, that the two layers don't bond together, because otherwise you end up effectively with a cold joint forming between your different layers. So there are quite a lot of things that we're trying to juggle in the process of 3D printing. It can be, from a material perspective, quite a complex exercise. Reinforcement, always one of the next questions people want to know about. How does that work, and how is the nature of the concrete behave in a long-term effect? Well, normal concrete is isotropic. So you have the same properties in all three of them, your main axes, but printed concrete is considered to be highly anisotropic because of the layers and the nature of the printing process. So you tend to get different strengths and reactions in the different directions, vertical, horizontal in the direction of travel, and even horizontal perpendicular to the direction of travel. So when you're doing a structural design, this all needs to be taken into account. And what it can mean is that your standard concrete design equations do not necessarily apply when you're looking at 3D concrete printing. Now, a lot of the time, we actually use printed concrete as compression-only structures, or occasionally even as interestingly shaped formwork, which is then reinforced and cast inside conventionally. So we refer to it as lost formwork shapes. But it is actually a structural element itself, and it is structurally sound. There are numerous different ways of reinforcing it. There's a lot of development which is going on continuously on this matter. So just as a brief overview, they are typically split into reinforcement which is done pre-process, so that involves combining items into the mix, for instance, including fibers into your mix, to single-step processes. These are reinforcement elements which are added typically by the robotic machine during the printing stage. So sometimes there is cables or elements which are entrained and extruded at the same time as the actual mix. Sometimes there are bars which are placed down between the different consecutive layers. Sometimes there is, you effectively screw the reinforcement in across the layers as they're being cast, maybe even even welding them together on the consecutive layers. There are quite a few single-step processes that can occur. And then you also get two-step processes where you, for instance, cast your concrete elements and then just as concrete elements, and then you might apply a post-tensioning system after the casting process in order to bind them all together and give it that ability to be able to withstand the tension as you would for many other post-tensioning elements. Now, I'm probably at the moment making the whole process sound very complicated and challenging, and that is not my intention. So the question is, why should we bother with 3D printed concrete at all? Okay, well, aside from the inherent coolness of this, which it is, the coolness is quite strong, there are very tangible and practical advantages to 3D printed concrete as well. So firstly, it needs no formwork. Now, for those of you who've worked with structures, you know that formwork is one of the most time-consuming and costly elements of creating a concrete frame. This dramatically increases the more interesting your concrete structure gets, especially if you're trying to build anything which is not rectangular. I remember losing days of my life on one project in particular, where we were trying to get the real-life formwork to correlate with the admittedly exotically angled structural model in a way that would actually allow us to cast it, and it was an extremely difficult process. There are complications, there are restrictions to what you can print without supports, especially when you're looking at things like overhangs. But overall, this ability amazingly speeds up the overall construction process. When you're not limited by what your formwork can supply, you also end up with one of the other main advantages that the architects love, which is your flexibility. Suddenly, all of those shapes that final year architectural students randomly come up with to try and revolutionize the industry actually become a lot more feasible, whether it's a decorative facade panel or exotic tree-shaped columns. Now, at least from a material perspective, that is a viable option. Then there's the question of speed overall. Now, speed is one of the main selling points of 3D printed concrete. There's no denying that it is faster than building a home out of blockwork or brickwork or putting up formwork and then casting conventional concrete. But it is obviously still vulnerable to all of the same casting issues you can have with conventional concrete. Machines can break, pumps can get blocked, issues can occur in the mix. So these are obviously no different from what one would normally encounter when doing conventional concrete. Another one of the advantages, the machine can literally not print it in the wrong place. We're not quite yet living in a Terminator world, so if it's not thinking for itself, if it prints concrete in the wrong place, you have given it the wrong instruction. This really does help, especially when one's working on construction sites where the quality control might not be where one would prefer it. Sustainability. We all know concrete is not the world's most sustainable material. It's a significant contributor to carbon emissions all over the world. So understandably, there's a huge push on and pressure on to find ways to reduce this. Renewable, recycled materials, reducing the amount of concrete is one of the main ways. So because of the way that we are currently casting concrete, there's actually quite a lot of wasted material. Anyone who's done a beam calculation can tell you that most of the concrete in the tension zone is really there just to hold the reinforcement in place. But with something like this, we can now create a system where the form can follow the force, because you can put the concrete where it is needed to be. Incorporation of late changes. Well, we all know that design freezes are occasionally mythical on a project, but we would still love them to happen. The ability to print concrete gives us a little bit more flexibility in this regard. For instance, if you are now trying to print 100 facade panels, you can, within reason, change that up to the last hour before the actual printing happens and still not have too significant a delay on the construction process as a whole, which is not something you can achieve in many other forms of construction. However, it doesn't mean that you can just randomly not have any form of design freeze, of course. It just gives us a little bit more wiggle room during standard construction projects. Then these last two, I'm going to cover in a little bit more detail in just a few slides on. So hence the question marks next to them. Okay, let's talk about where we are currently using it though. What are the markets for 3D concrete printing? Well, they're being built all over the world right now, from earthquake-resistant structures in South America to multi-story apartment blocks in China. There are bridges, there are what we typically end up calling furniture, so benches, chairs, pot plants, all of that sort of thing. And there are exhibition pieces, so particularly interesting organic shapes which are made. One of my favorite facade panels is this picture on the right-hand side, which is being made as a joint venture between those architects and TU Eindhoven, where they are looking at concrete printing these amazing facade panels with double curvature on. It really showcases a lot of the interesting options that this new technology provides us. Now, I would say that the vast majority of the work which is being done at the moment is more in the prototyping stage, except possibly when it comes for single-story houses. They are now effectively moving out of the prototyping into the more widely accepted stage. I am hoping that the video here is portraying fairly smoothly, but this is a video that was taken by John Burns. It's of Wolf Ranch in Georgetown, Texas. Now, this is a neighborhood of 100, well, I think they've actually technically only built 92 of them at the moment, but 100 3D printed single family homes. The entire neighborhood is 3D printed. And it's a fascinating example. The first 8 or 10 houses took quite a long time to get them going while they sorted out quite a lot of the logistics. But the rest of it, once they organized their patterns and their systems and approaches, sped up remarkably. And in these things, the people bought their houses off plans, but they still had quite a lot of adaptability between them, and they could pick and choose differences in how they approaches that they wanted. So you will see a lot of these houses look similar, but actually quite a lot of them are quite different from each other too. Now, going on to costs, because they're typically one of the more controversial items. How expensive is it? So in some ways, it is cheaper than conventional concrete. Overall, you are using less concrete in the structure as a whole. The advantages from the time-saving systems are considerable because you get all of the knock-on effects from the P's and G's that you're saving in the construction as well. You also get the advantage of the accuracy, so you don't need to wait. For instance, if you're putting in precast floors or timber roofing, you don't need to wait to measure anything up. You can order it based on the planned or modeled accuracy because they are sufficiently accurate enough that you can go straight, and that additionally saves time on a project. On the other side, it is new technology, and because it is new technology, there are elements about it which are more expensive. There are high capital costs, so the physical buying of the machines itself is at the moment quite expensive. The material, you need to find local material which is suitable for doing the printing. The further that you have to move the material, the less cost effective it ends up being. Training, there's obviously, with new technology, there is training that needs to happen on site. The first printing that people do tends to be a lot slower. They speed up as they become more comfortable with the technology. And there is obviously transportation and logistical expenses associated with setting up the equipment itself. So right now, it's not very easy to say whether it's cheaper or more expensive than conventional concrete. It very much depends on the situation. But it is certainly not excessively more expensive than conventional concrete at the moment. Right, so societal ramifications. Now we get to the tricky parts. I think probably the single most common question that I get asked whenever I tell people that I'm researching 3D printing is, will it cause job losses? At least in South Africa, that's what I get asked. Now, overseas, a reduction in labor requirements is seen as an advantage of 3D concrete printing. This is not considered the same way in South Africa, or in fact in most developing countries. Overseas, they don't necessarily have sufficient in the way of labor market. So for safety reasons and for quality reasons and for a simple lack of people, they are trying to reduce the number of people on the site. In South Africa, that's not the effect that we are trying to create. Now, here it's tricky. There aren't as many studies to be able to quote from. There is some work, for instance, I know the University of Johannesburg is doing some work into the technological acceptability of this technology within South Africa. But if we go from an opinions perspective, and to my opinion, a lot comes down to the implementation. If you look at the way that the US systems are trying to implement 3D printing, they are trying to reduce the number of people on site. They're looking at about 4 people per printer for the gantry printers. However, if you look at certain companies like 14 Trees, which has been printing houses and schools all around Africa, they have a totally different approach. So they still have quite a lot of people who are working on the site with the printer. Where they gain the advantage of the 3D printing is less from the reducing the people on site and more from they do the services integration and keep the printer moving at the same time. Whereas on the American side, they typically pause it and then do a run through of services integration and then carry on with the printing again. So that helps them to be able to print quite fast and quite efficiently, which has its own benefits. Now, you still obviously have all the other people employed on the site to do all of the other integration work that would normally occur. Now, the point of 3D concrete printing is not to replace all uses of concrete. That's simply never going to happen. But it does have substantial advantages for particular use cases. And the idea is more to use it where it plays to its advantages. Now, when it comes to will it cause job losses? Well, if it is used for housing, it will need fewer people making concrete blockwork. If it is used for larger structures, it will need fewer people working in the formwork side of things. At the same point, it will need more people to operate, understand, and use the machines, and it will still need all of the adjacent skills and trades which are necessary for the structures. There are also the possibilities of spin-off productions here. What you might not be aware of, for instance, is I used the example of 14 Trees earlier, and these are the images are from 14 Trees' webpage, but they've actually collaborated with a company in Boksburg called PMSA, where they've made their own 3D printer, which called Oroko, which is currently commercially available. So the fact that in South Africa we are capable of making our own 3D concrete printers is a fantastic thing which can spark and develop its own industry. I will say it's a particularly difficult topic to talk about the societal impact of this, though, and definitely should not be underestimated. And maybe we'll discuss it in the panel going forward. But from my side, last couple of things to look at. Where to from here? Well, I've included, this is actually now a slightly outdated picture of our one of our printers at Stellenbosch. This is a printer that we created at Stellenbosch. So it was made by the students and lecturers at Stellenbosch. And it's one of the 2 printers there, both of which were made by the people involved. And here we are doing a massive amount of work and research development on all sorts. It links with research studies which are being done all over the world, from integrating reinforcement, mixed design, durability, fire resistance, how to develop the new standards, how to incorporate it in existing systems and integrations. There is a massive amount of work still to be done, but it is very exciting and very promising what we're looking at. And who knows what our structures may end up looking like once we've managed to get this all working and working smoothly. So that is it from my side. Thank you very much for listening to my side, and I will have a look at any questions there might be in the chat.
Thank you very much, Kim, for that. And I think a good follow-up to Brian. So you have shown how robotics in their simplest form can be quite productive. Thank you for that. Our final speaker for this evening is Mr. Ricardo Lopez, Ricardo completed his BEng at UJ in 2016 and has also completed his STC20 at the School of Concrete in 2019. He started his working life with WBHO as a junior site engineer. He then did a short stint as a teaching assistant at the University of Johannesburg. He must have seen the light and realized red pens is not for him, so went back into industry, joined Mapei South Africa as a technical sales consultant, and he joined DeltaScan, who he is currently working with in July 2022. The topic of Ricardo's talk tonight is infrastructure management through digital intelligence. Again, please show your appreciation for Ricardo and welcome him to this evening session. Ricardo, over to you.
Awesome. Thank you so much. Look, sort of quite excited to be presenting this evening. I hope everyone can see my screen.
All good, Ricardo. Sound and vision good.
Fantastic. So yeah, thank you very much. It's always a pleasure to be involved in SAICE's webinars, and especially this one being such an innovative topic. Looking forward to showing how perhaps DeltaScan is implementing a lot of these digital in sort of advancements and AI and so on in the industry we all kind of work in right now. So when we jump into it, just a quick background on DeltaScan itself. DeltaScan is a company that started by engineers, and essentially it's for engineers. We focus on data analytics by digitizing the world around us. This allows us to conduct inspections and surveys with unparalleled accuracy and efficiency. So we've started in South Africa, we've branched out globally, and believe it or not, we find that the more work we actually do overseas, we realizing that we're almost a trendsetter in this environment, and it's quite exciting that, we always think that being at the tip of the African continent, that perhaps we get things a little bit late, but we're finding quite the opposite as we venture more into this service. So digitization and implementing it into the engineering landscape, from DeltaScan's perspective, we place that into 3 services or 3 environments where it's possible. Currently, we do a lot of scan to BIM work, which is recreating Revit or as-built information through laser scanning. And we then move into the inspection landscape. So developing what we refer to as digital replicas from real world infrastructure examples, silos, chimney stacks, whatever they may be, recreating them with textural information, with all the visual information that's necessary to actually analyze these structures, and then of course into the surveying landscape. So the value that digital intelligence in infrastructure management, so the way it adds real value is by creating efficient operations. So optimizing workflows, allowing us to predict failures before they happen and avoid perhaps repetitive or tedious tasks. We're able to move through that quite swiftly. And this naturally moves us into a position of proactiveness instead of being reactive to scenarios. So we therefore avoid the costs of unforeseen issues, and we can move into a space where we're predicting what needs to happen next and planning and budgeting correctly. We can, by implementing this on a regular basis and also through the use of IoTs, we can move into a space of real-time monitoring and analytics. So that means we can even move into a place where we create efficiencies in the actual productions or the actual running of a plant or a facility. And that naturally speaks to sustainability and environmental impact improvements, making sure we're leaving a better world behind us. So how does this actually work? How do we implement digitization into infrastructure management? So it starts with data collection. So that's the foundation of all the intelligence, and it needs to be accurate and it needs to be comprehensive. And from our side, it can be anything from an IoT device to a laser point cloud to drones giving us information, and that's where it all starts. From there, we can analyze this information with the use of a hybrid AI approach. So that's software and artificial intelligence that helps us find issues and forecast future issues that may be present or lurking behind us. We then can transfer this data into digital twin technology. So recreating that environment in our comfortable air-conned offices. It allows us to run simulations on that environment. It allows us to expand on a piece of infrastructure or decrease the size of the infrastructure to optimize decision-making processes. And once again, moving from a space of reactiveness to predictive maintenance. So proactively thinking about what's going to happen next. And this all at the end of the day leads to automation and essentially moves professionals into a supportive role. So allowing digital information to actually take control where we as the professionals are guiding it and making sure it's doing the right things where we need it. So from a Delta Scans perspective, scanning technology and drone technology form the backbone of our business. These, at the end of the day, are the different hammers that a carpenter may use. We're not going to use a hammer to obviously screw in a screw. We'll be smashing in a nail for sure. And then sometimes we need a drill. And that's the point of this slide, is to show us that this is the backbone. But at the end of the day, it's the tool. And what we really focus on is the data that these tools capture. So drone technology and LiDAR technology or terrestrial data capture on laser point clouds, they can meet in that point cloud space. And if we're not familiar with point clouds, I'm hoping the slide will give us a little bit of a background to what that might be. So laser scanning and point cloud technology, essentially light detection and ranging is the technology. It sends out a pulse of light, and that light reflects back to the machine and assigns that point an X, Y, and a Z coordinate. The example I like to use is when we know what a cloud is made of, an actual rain cloud. And if we zoom in close, we'll find little tiny droplets that constitute a massive cloud. When we step back, it looks like a solid object. And a point cloud is actually similar in nature. So once we conglomerate a whole lot of points, we can kind of see a solid or a big object. It's then up to us as the technicians to translate that point cloud into something usable. So point clouds are very, very valuable, and capturing their information, we can do it using a variety of tools. So we can use a SLAM LiDAR unit for mobile applications for quick turnaround times, but we sacrifice a bit of accuracy. If we want to look at very, very high detail, millimeter accuracy point clouds, we need to look at phase shift scanners. Something static takes a little bit of time to capture that environment, but we can literally recreate in millimeter accuracy what our site has. What that can do is be merged with photogrammetry point clouds. So taking a drone, flying it over a site, capturing hundreds of images, maybe thousands of images, and instead of stopping our inspection or our workflow there, we then, through a process of photogrammetry, stitch those photos together. Those photographs allow us, because we're taking at different angles, at different altitudes, with the perspective obviously being on our major points of interest, that allows us to actually create depth in our models. And we therefore have the ability to take laser point clouds and photogrammetry point clouds and merge them together. And now we're starting to enable engineers and technicians to really start getting into some nitty-gritty information. So what are the challenges that this kind of technology and how we capture it, what is it mitigating? Well, at the end of the day, what we'll eventually do is eliminate the need for reactive maintenance or reactive problem solving, because we'll have the ability to capture our environment readily. So in other words, very quickly we can mobilize the site, very quickly we can capture that site, and quite quickly we can develop the digital models that we need to then go through the BOQs and developing the methodologies in repairing that structure. We also mitigate the separation of professionals. So data silos become bridged. We can have, different professionals all speaking in one environment off of one model. We eliminate the necessity for the manual monitoring, which is historically quite tedious and quite time consuming, because we can mobilize the site quickly, capture quickly, we can turn around reporting a lot quicker than before. This naturally allows cities, it allows specific plants, it allows mines, whomever, to scale better than ever before. Because the information is readily available, we can run simulations, whatever the client or the end user needs from that bit of information, we can get a lot quicker, and eliminates, at the end of the day, resource constraints. So that could be skilled resources, or it could be just general resources. So how does DeltaScan develop their recipe? So we start by taking our point clouds and registering them. So that means taking all our multinodal data capture and merging it into one single piece of data. We then segment that data. In other words, we can find different objects, we can separate surfaces, or we could add surfaces. We then go into the reconstruction phase, which is texturing, or sorry, triangulating and meshing, and then texturing that information. And that then allows us to actually look at features, important features. So before we start getting into actual examples, let's just think about the applications. So from manufacturing to quality control, so in other words, construction monitoring, clash detection, all the way through to architecture and engineering, so literally looking at how to rehabilitate structures or preserve structures. We can even go into forestry and agriculture, but perhaps most important is archiving and documentation. So having all this information digitized means it's light and doesn't stand a chance of disappearing in archives or getting stuck in a file room that eventually gets flooded. So let's delve into a couple of examples and what this technology might look like. So scan to BIM starts with merging of data clouds, of point clouds. So this is a point cloud merged with aerial data footage as well as terrestrial laser scanning. And as you can see as the video plays, there's like these little points, and it's not quite a full picture yet. But from this, we can develop our 3D Revit models, our actual digital twins. These are smart models that are capable of having BOQs developed off of it, columns, windows, whatever the case may be. From here, it's a place where all our different professions can meet: landscapers, architects, engineers. And this can be done on a commercial space, but also in highly technical spaces where piping is very, very dense, ducting is very, very dense, and we want to know everything about this particular structure, even bracket sizes, bolts and nut sizes. This is the power of laser technology and eventually taking it into a workable CAD space. This progression is really becoming so valuable to a lot of professionals. The accuracy in which we capture information is one step in this equation, but how we develop the information and show it in the CAD space is also important. So it's important to note that there's different levels of development that's possible from these different types of data capture. So if we're looking at quick turnaround times, we're looking at basic geometric information that's needed on a project, we're going to be looking at LOD 200. But we can go as detailed as LOD 400, which includes GPR scanning to find out what kind of rebar structures we have in place, and high precision millimeter accuracy LiDAR scanning to merge those to find LOD 400 development drawings and plans going forward. What does surveying tools, or how has surveying been impacted by digitization? And this is a small example of what that might look like from a DeltaScan's perspective once again. We can take an environment, a large environment, and put it in a place where everybody can communicate. So it means that, again, our architects, our engineers, our town planners, whomever is important on this project, gets an opportunity to view all of this information. This is information captured by a drone. This information could be captured on a regular basis or a once-off. And this creates point clouds, it creates orthophotos, where we can literally go from measuring, straightforward distances to actual volumes. We can go into the 3D space here. We can see elevations on our environment for planning purposes, for an event, or for future project expansions. This is the power of simple implementation of digitization on a site. So let me just go, yeah, there, sorry about that. Okay, we can get into a little bit more detail as well by actually understanding that from a point cloud, we can do production facility grade information. We can optimize the way that our production facilities are actually operating. So by digitizing the full site and putting it into a workspace that anybody can use, we're able to analyze stockpile assessments. We're able to even go larger than that. But by simply understanding that from a point cloud, we can draw a simple polygon and generate a volume in a matter of seconds. That's the difference that digitization is adding to production facilities. And this can even be applied to landfill sites. So understanding, what has the contractor perhaps been doing over a space of time? We can do massive volume checks and also compare it over time. So change analysis and understand if maybe a contractor's claims are correct. This heat map will show where the contractor has been working and where they haven't been working. And this is just a simple application, again, of digitization that's happening currently in South Africa. So what about inspections? What about digital technology in infrastructure management? So this is the old way of doing things. And, up until now, it's worked and it's served its purpose. But there are inherent challenges with this. With rope access and so on, there's huge health and safety risks. There's a tedious nature in which the inspections occur, which means that there's long shutdown times. And this naturally adds to the cost, not just of actually conducting the inspection, but also by having the plant not running. And at the end of the day, we find that sometimes there's really minimal value in the reporting. We end up with files like this, and honestly, we've been there, and this is why we've progressed into the next phase of inspections. So what does that look like? So we mobilize to site. We take a drone with us, and we capture an entire AfriSam piece of infrastructure like this. That's a 75-meter tall structure in half a day. So half a day, we've captured the entire environment, and we generate this, a 3D textured replica of the asset. This comes with all the cracks and all the delaminations that we've seen on site. You can see them zoomed in so that you can get all that detail and understand exactly what's going on, but also take a step back and perhaps see if from a different perspective, these cracks are behaving in a certain way. I'm pretty sure we could find an ant on this if we really tried looking at it long enough. But this is the power, once again, of digitizing environments, because now multiple engineers and specifiers can take a look at this piece of infrastructure without mobilizing all the way to site. We've now got the ability to do our inspection from an air-conned office. We can see honeycombing, we can see delaminations, we can see all the cracks necessary, and it doesn't matter if the surface is concrete or steel, we'll see whatever the defects are. Once we extract this value, so this is where AI and specialized software gets involved. By extracting elevations of the structure, we can now annotate the defects. We can localize them, we can find them, we can put it on a 2D facade map, which is, in my opinion, like a roadmap for the future contractor. They know exactly what the problems are. They can quickly ascertain how they'll need to solve them. And most importantly, is we can quantify them. So there's no more guesswork. There's no more overestimation. But that's the power that artificial intelligence adds to digitization. And what about seeing beyond the surface? So by putting a thermal drone, thermal camera on our drones, we're able to actually assess structures for delamination a lot more accurate than we have in the past. Instead of a rope access team hanging off of the building, knocking on the surface and estimating the delamination, we can now precisely give an area of delamination through thermography. And we can couple all of this information into the previous seen video. So on a large scale, say perhaps on a big facility, on a mine, on a refinery, what might this look like? This is an example of coupling different modes of data into one model. So we've gone in here, there's laser scanning that's happened on the ground, there's aerial LiDAR, there's also aerial photogrammetry that's happened on the site. And we now have a full site digitization where we can measure, we can annotate, and we can talk. But not only that, we can actually incorporate the terrestrial scanning and the CAD models that have been generated as well. This is what it would look like in the RGB space. So now the full 3D textured model can be looked at for corrosion, for all kinds of defects that may be happening on site. And this information can be assessed on a regular basis. There's no necessity for rope access teams, cherry pickers, and engineers to come out, every couple of months to look at different pieces of infrastructure. We can capture it in one mobilization in precise, crisp, and clear detail. So that's what it looks like on a grander scheme of things. And perhaps confined space becomes an issue. All passes, mine shafts, silo bins. The new world that we live in of digitization allows us with one piece of kit to capture all kinds of information. So what we're going to show you at this point in time is the Helios 3. This is a drone that is both coupled with a thermal camera, an RGB camera, but also a SLAM LiDAR unit. So converting or combining all our data modes or potential data modes into one device. We can now fly into environments that are dark, that are dusty. We don't need to put people at risk. The drone enters with no issues. And once we are inside the environment, we can see everything crystal clear. With 10,000 lumens of light, there's no issues, no place is too dark. We can have a look at the structure and we can assess the structure now in more detail and without putting people at risk. So that is what happens now when we keep adding on valuable data capture techniques with our new way of reporting. So let's combine an external data set. So this data here captured by an external drone, all our photogrammetry techniques here, we've created this digital replica, we've annotated it so that the professionals can see what is wrong with their structure. But not only that, is we've also been on the inside of the structure. So we've mobilized to site with 2 drones. We've gone external inspection as well as internal inspection, which you'll see in a minute. Let's just jump ahead here. So here we go on the internal inspection. And we now get a better view than ever before. We can see, we could even do a stock take using the LiDAR on this drone as well. But we can now see the detail inside and out. And the beauty here, the beauty of this comes really in the reporting. So we can now do facade maps that overlay or overlap on one another. So we can see the crack propagations from the external facade and how they behave on the internal facade. That is the power of digitization. So we've also been involved in some high-profile projects, including the collapse of Kusile. I'm not showing anything that's not in the public space anymore. So, oh, that's a bit loud. Sorry about that. So this is what digitization does for emergency response. In this situation, we know the whole country is in crisis. Right now, the biggest power plant in the country is at a standstill because of what's happened. How do we get there? And how does the professional team decide on a way forward? So we mobilize the site. Doesn't require too much, really. It's just our drone in the back of a bucky and off we go. And now we can start giving engineers some incredibly valuable information. We can start showing the end user and the client, hold on, we now have identified why this has happened, why the collapse has occurred, because this massive chunk of fly ash, which shouldn't really be here, has actually fallen off, dislodged, and hit the bottom of your lobster arm, causing 3 units to go off in your power station. So this is the first response, and identifying the problem. We can then take it offsite and start analyzing the problem and going, okay, is this a problem that can be fixed? Should we be risking it right now? Should the structure be condemned? This is real questions that the client was asking us. And from the digitization of the structure, we could give the client those answers much faster than if we had to have relied on who knows what, because there certainly wasn't going to be a rope access team or cherry picker to go up here. So what we realized was these flues were supported by 3 main beams, 150 meters up in the air. And we needed to communicate to the professionals whether this beam was in a current state of failure or plastic failure, or how was the structure behaving. So by mobilizing with our high-tech little gadgets, we're able to capture visual information on connection details to understand if those are behaving like they should. But not only that, is the point cloud that you can see on the left-hand side of the screen is going to give us perhaps the most valuable information of all. So once we've concluded the on-site work, which is a couple of minutes really, we can take the information off-site and quickly extrapolate and give valuable input into what is the structure doing? Is it behaving like it should be? And analyzing if these beams are deflecting. So we could understand if these massive beams are behaving and still holding the structure up like they should. And that's the power of digitization. So we can then go into disaster preparedness as well, which is perhaps an example of how this is impacting society. So perhaps we mobilize to site, or, you know, on a regular basis, we know that a certain river overflows and impacts a community. So we need to understand, perhaps as professionals, what kind of impact does that have? How many people stand a chance of losing their lives, losing their homes? And so by a simple survey, so throwing a drone up in the air and capturing this environment, we're able to recreate that environment. We're able to assess that environment with multitudes of professionals being involved in the project. So we go into this environment, we can pull up the ortho photo, we can even count how many residents perhaps live in this environment by counting through the use of artificial intelligence, counting the amount of structures and informal structures in there. We could estimate the amount of people that are actually living along this riverbank. And from here, we can start running a couple of tests and checks and understanding, you know, what is the volumes? What are the areas that are potentially here? What kind of impact currently does the community have on this river? So perhaps, you know, there's a bit of illegal dumping going on one side, but there's also people trying to clean themselves further on downstream. What kind of impact are they having on one another and the community having within itself? And then lastly, we can jump into understanding perhaps the most important here, which is how does the river behave when it floods? How many people stand a chance of losing their lives, losing their homes? And this is the kind of information that you can achieve by an hour over a site and taking that information, digitizing it offsite and running these simulations. And what you'll see from here is we're able to then generate cut-throughs of this environment, understanding what the riverbanks are actually looking like and if there's any danger of collapse there, but also in this image here, which is the most risky areas in terms of a flood occurring in this area here in the blue. These people are all at risk in this situation, and these are the impacts that we can avoid and mitigate through the use of digitization. And this is all then possible through Delta Cloud, a online platform which is not tied down to computers that need special graphics cards or anything like that, but we've moved not only just to digitization, but digitization in the cloud, allowing people to access this information readily as long as they have the right credentials. And this could be any piece of information on the infrastructure, whether it's a surveying project or infrastructure like a chimney stack or a silo process or a plant that we need information on stock and so forth. And this culminates into engineering reports being available for deflection checks, deformation checks, environmental impacts. And this is all available on a cloud. So no more tying down to a massive computer or massive rigs to run this. And from a Delta Scans perspective, you know, we've been doing this, you know, unbelievably for only about 4 years. And this is just the beginning of this implementation. And we're super excited to see where it goes, but also be one of the guys leading the way. So from my side, that's all. And I hope that I haven't bored anybody and lost anybody's attention, and happy to take questions. So thanks once again to SAICE and for everybody for staying on. It's awesome to be a part of today.
Thank you very much, Ricardo, and to Brian and Kim. Ricardo, I've got one or two questions for you in the chat, and then I'll circle back to Kim and Brian. I see Kim has been responding. The question is from Sesakani, who asks, how is the data quality ensured and validated?
Perfect. So from a data validation or quality perspective, at this beginning stage of this technology, there's still very much professionals that walk the road. So when we look at, say, for instance, the essence of all of this is actually surveying. So what we're doing is capturing a real world asset. So by simply putting ground control points and having a surveyor ascertain those ground control points and sign off on those ground control points, there's actually, that is the quality check and validation that is spot on. It helps for us to make sure that the infrastructure, the ground that we're assessing is in the right place and exactly to the millimeter accuracy in point cloud technology. There is, of course, this on its own can be quite a topic, but there's the understanding that LiDAR, so terrestrial fixed point scanning, the millimeter accuracy is there. But the moment we start moving into mobile scanning and even photogrammetry, there is going to be noise in that point cloud. And that's why it's exceptionally important to do ground control points. So we know that there's still, at this point in time, the necessity for surveyors and engineers to be involved in the workflow.
Thanks, Ricardo. And then I think Kim is just trying to ensure you're on your toes here. She has a question for you, and that is the point cloud automatically converted to structural elements, or does it need manual intervention?
So at this stage, when we convert into a let's call it the digital twin, which is our CAD or Revit packages, there is still manual intervention. So although the process is much faster than mobilizing to site and taking measurements with a tape measure and sketches and so on, there's still manual intervention. There's still positions for engineers and drafts people involved in this. And I think it leads to the point that Brian even said, which was you won't be replaced by a robot, but you'll be replaced by someone with a robot. So that's where we currently are.
Ricardo, there's a few more questions, but I wanted to just ask a generic question.
Sure.
And maybe Brian can have a first stab at this one. You are still awake, Brian. I know we're keeping you very, very long time from your bed. Good. How can we coexist with machines that inherently lack human values? Is that too philosophical? So I said, how can we coexist with machines that inherently lack human values?
Okay. We're looking at two stages in artificial intelligence. One is artificial general intelligence, where the robot or the artificial intelligence does not understand that it is not human. That's 2 to 3 years away. 2 to 3 decades away, we'll reach the stage where artificial intelligence is sentient. It realizes that it's not a human, and life may well become silicon and carbon. In other words, we may merge societies.
Okay, and then if you were to consider, what would be the most important values that we should embed into AI?
At this stage, AI is running on its own. We no longer have the capacity to control it.
So does that mean that we can't teach machines, and robotics and 3D printing are effectively machines, ethics, empathy, or compassion, or is that something that will come?
You can do that on an individual basis, but there will always be a rogue machine which will ignore you.
Okay, so I suppose the question then is, and you've sort of inferred, What happens when a program that can rewrite its own code diverges from the intentions of its creator to achieve a specific goal, its intended purpose?
That was my question mark at the end of my talk. We do not know. You can ask the cleverest people in the world, and they cannot tell you where we are going.
And then particularly given, in our case, high unemployment and poverty and things like that, not only South Africa, but the continent, do you think we can prevent certain populations from being discriminated and or marginalized by AI and robotics?
The richer countries will benefit, the poorer countries will not. That's an unfortunate outcome of technology. But South Africa is faring quite well. We're 6th on the use of ChatGPT in the world. So obviously there's a lot of people in South Africa who are using ChatGPT and other artificial intelligences. So the more that we can stitch into artificial intelligence and robotics, the better outcome we will see. Other countries in Africa may well suffer, and there's no doubt that jobs will be lost, but we must work hard to replace those jobs with new jobs that
Brian,
do not exist at present.
Your comment about South Africa being so high on the list, that may explain why in many of the EXA rejections in window 1 for 2024, a large number were rejected on the basis that their reports, both TERs and engineering reports, were generated by AI rather than by the actual submittant. So it's a good thing, but it can obviously be a dangerous thing. So
yes, it can be.
Anyway, I think we'll wrap it up there. To Brian, Kim, and Ricardo, again, our sincere appreciation. I just wanted to check whether Simon or Shadrach wanted to wrap up the session for us. Hopefully your expectations were met and you were as entertained as the rest of us by our three knowledgeable speakers. And the world and the future of the world in some respects is quite scary, but also quite exciting. So Simon and Shadrach, I don't know if you have a few words to add. Don't be shy. You don't have to speak. I'm just checking. There we go. Simon, please, over to you.
No, I just wanted to say thank you very much. We truly appreciate it. These conversations are very key for us to have amongst professionals, and it should also reach the public as well so that they are aware and start applying their minds as they use any kind of technology. And this is quite a very interesting topic that we had. And wow, from our side, we learned a lot. And thank you very much.
You're most welcome, Simon. Mems, anything from your side as our careers fundi? I've caught memory by surprise. You muted, Mems?
Sorry, just thank you very much to our presenters for their willingness to do the presentation for us from career side. I think it's very interesting. I'm just in the hindsight, I should have invited schools as well that took part in our competitions. Next time I'll definitely do that. And thank you very much, Tom, as well for your organizing of this event for us.